Welcome David Shipworth, who is a Professor of Energy and the Built Environment at UCL Energy Institute and co-lead of the ESRC Behavioural Research UK Leadership Hub theme on environmental and sustainability. His research focuses on how people use technologies to turn energy into the services they want, such as comfort, mobility and cleanliness. And his interests range from how individuals interact with technologies through to how communities form consensus around socially good outcomes. Without any further ado.
Right, thank you very much. Right, I'm going to set, I think it was like 35 minutes plus Q&A. If you don't have one of these things, I strongly recommend installing one on your phone. They're also brilliant for students, so that you stick them in front of a student and they stick to time. But they work for professors too, apparently. Okay, thank you. It's kind of, I find this really interesting, and the whole concept of this is something I wish I'd bumped into back when I was doing my PhD. So I congratulate the organisers. What I'm going to present is a kind of slightly different approach. So I'm not a mathematician, but I've tried to use maths to solve problems that I'm interested in. So I tend to kind of rummage around in the kind of mathematical toolbox and try and find something I think is an interesting fit, and then employ somebody with enough brains to apply that to the problem that I'm working on. So that's the kind of approach I've taken. And what I'm doing here is I'm going to walk through the range of different kind of formalisms that have been used to try and think about the representation of human behavior in the energy field. And it's quite idiosyncratic to me, and I've leaned into use of Claude quite a bit to kind of iterate this. So just for kind of transparency, what I did is I actually, yeah, sure. I put together a bunch of references and about a 2,000 word prompt, which I fed into Claude. And then I got it to iterate and work with me, produce a Word document, which I annotated and fed back into Claude. If you haven't tried doing this, it's really useful for the exploration of thinking. And I quite strongly recommend that. Let's see if I can get this to go down. Should this be down arrows on the keyboard or... Oh, a mouse. Thank you. Right. Okay, so the first thing I think is basically there's a famous quote that a colleague put out, which is buildings don't use energy, people do. And there's a tendency to try and model energy and energy use. And from a human behavior perspective, that's the wrong starting place, because nobody wants to interact directly with either gas or electricity. It's usually a lethal combination. So basically, people want to buy a bit of technology where they feed energy in at one end and something falls out the other end that they want, like the World Cup or clean washing or something else that's actually a useful service. So what you really want to think about is services. But services itself is a very kind of economically framed concept. So what you want to do is actually observe what people do before you start walking in there with some preconceived notions about people wanting services. Because we tend to think about things like transport modeling, and we tend to say, what is the service of transport modeling? Well, it's something like passenger kilometers. Now, if people bought cars based purely on passenger kilometers, everybody would be driving around in some kind of very minimal car, but they want all sorts of other social services. They want prestige, they want adrenaline, they want a whole lot of other things. So think about what people do and why they do it. So that is a kind of plea to kind of get out of and break out of the kind of standard ways of thinking about this and really go back to thinking about the people and what the people want. And it's always worthwhile thinking about yourself and your family. I've had no end of discussions with policymakers and others who model humans as economically kind of cost-rational agents, and then ask them, how their teenage kids behave and say, oh, your teenage kids always do this. And they go, oh, no, it's impossible. No, it never works. But I'm going to apply it to the rest of the population and assume that works. So, yeah, don't get too carried away with disappearing into the kind of theory of the models. Okay. Couple of starting points. I always fall back to a couple of these definitions, which I found exceedingly useful for thinking about modelling. The first one is from a guy called John Casti. I don't know whether that's a familiar name. He wrote really a couple of great books called Reality Rules. There's volume 1 and volume 2. And it's still my kind of go-to guide for an overview of mathematical methods that can be applied in a large range of different areas. So he has that first definition. The other one is from the model theorist Winsberg, who basically talks about computer simulations and says they have these 3 characteristics in that they are downward, motley, and autonomous. And basically, in applied areas like trying to model energy and energy behavior, we tend to come up with what I've called a kind of, sort of epistemic sausage machine. We just throw loads of different bits of data and theory and everything into it. We grind up this thing and we produce some kind of model that falls out of the back of that without really understanding what it looks like. And this is kind of what Winsberg is trying to capture with this quote. And it's very common, particularly as we build larger energy models, which include human behavior, but include the systems of, how the system operates, a whole lot of technical, economic, and behavioral elements. So I do think it's useful to kind of try to understand these artifacts, and I'll come back to that again and again about what these artifacts are that we're trying to build in terms of mathematical representations of human behavior. So for this talk, there's a couple of ways of thinking about this. And again, I said this is a breadth-first approach. The first is to distinguish between models of human behavior and modeling with humans. And that latter category may sound a bit odd, but I know there are some here who've done work with this. But really, modeling with humans, I think, is really interesting. It's basically where you are collecting data from human participants that is mediated through some kind of mathematical structure. And this has been done, the classic way of working with people is through potentially things like Delphi techniques, where you're getting a group of experts together and eliciting their understanding about a domain. And there have been methods, which we'll look briefly at, where you interpose a mathematical formalism in there, like a Bayesian network, in order to have a common structure that emerges from that process. So here what we're doing is we're taking a mathematical construct and we're inserting it into a process of understanding how humans act. That's quite different from modeling the behavior of people. So the previous talk was more about we have data sets and we try to then construct a representation of the behavior of people from those data sets. So two very different approaches. In terms of modeling with people, there's also a distinction between models that try to do that in a very neutral way and models that deliberately set out to influence behavior. So once you get into the behavior change space, then you can think about the constructions of models, the purpose of which is to help a group form a consensus. Okay, so they are models which act within the world to change the behavior of people. And that's another class. Other things are around questions of the extent of aggregation. We've touched on that in the previous lecture. I'll be talking about the behavior of an individual or of some kind of intermediate level group like organizations or up to populations. That's a really important distinction. And also, are we trying to predict what the future will be, or are we trying to understand how to achieve a normative good outcome? So a lot of work in energy is about saying we want to decarbonize the UK economy by, 90% by 2030 or something like that. That is a normatively good outcome. And then we construct models that allow us to try and to explore how that might be possible. Two very different things. A couple of other considerations. Don't separate modeling from research design. They are completely interwoven with each other. So the types of data you need depends on the design of the research. I'll come back to this. Don't model it if you can't epistemically warrant it. So how many, the term epistemic warrant, people familiar, some people are familiar with the term epistemic warrant. Okay, important to understand what your model can legitimately make claims about the world. What forms of knowledge can your model produce, and what are the kind of philosophical basis for that? That's the epistemic warrant. When modeling people, I would suggest you always adopt a social realist position. So assume that there exist societies and forms of behavior, but that you can never know them perfectly. So there will always be degrees of uncertainty about your knowledge, and you need to be upfront about that and to try and represent that. The other point, which I think is really useful, is to get between your model and the world. So there is a space, a gap between your representation of the world and reality. You should have your model on one side and reality on the other side, and try to work out what the difference is. It's very easy to end up looking at the world through your model, and then all you see is your model. You don't see all of the errors in that. So try and intersperse yourself and really understand what the limits of your claims to knowledge are. For the next section, I'm going to run just through some of the different methods that are widely used in the representation of human behavior in energy models. The most widely used class is random utility or discrete choice models. So here we will typically ask people about what they value. We will give them alternate choices and get them to choose repeatedly which of these two outcomes they would prefer. So we end up with a data set that basically allows us to kind of rank order preferences of people. So this is your classic kind of economic approach. We've also broken that apart by moving into things like behavioral economics, where we start to make sets of assumptions, or we start to relax sets of assumptions really about perfect rationality, and say, well, we can observe from psychology that people act with what are euphemistically called biases. I find it very odd when economists think that if their model does not correctly represent the world, that the world is wrong rather than the model. But that's the way economics kind of looks at the world. And so humans are biased because they're not doing what our models say they should do. So we have to find ways to correct that. So we've got this set of approaches, important distinctions between like stated preference and revealed preference. So are you asking people what they might do, or are you observing what they have done? Really important and often very different outcomes. So that's one first kind of class of model, probably the dominant class used in the field, heavily used in sort of large-scale energy system optimization models and other areas. The second large class is basically agent-based models of various kinds. So this is the classic diagram from Schelling, who was looking at what could give rise to the emergence of forms of segregation in societies in America. And there's a lot of models that are looking at the world kind of from this interaction and emergent space, often informed by other forms of economic theory. So Elinor Ostrom has done a lot of work around basically collectively social good outcomes. There's a lot of work around opinion dynamics, how those change. So these are ones that are typically established in sets of agents in some kind of simulated environment where we encode those agents with sets of rules, and we press go and we see what emerges as a result of that. We'll come back to the kind of epistemic warrant of that in a bit. Another class of models are ones that are trying to work, if you like, more at a kind of mesoscale. They're looking at aggregate outcomes, at system level dynamics. This is the classic diagram from Giels et al., which is looking at socio-technical transitions. All of the references, I'll circulate a kind of paper which has all of the details and readings around this. But this is a kind of model of how we might expect new technologies to enter into a field and break it apart. And so basically the idea is that it works on three levels, a kind of micro, meso, and macro level, and that you've got a whole bunch of technologies bubbling along in the bottom, which then get early adopters taking them up, and then you get this progressive kind of potential for breakthrough into the main structures in the middle. So that's a kind of classic mixture of systems dynamics, diffusion of innovations. It's used in a range of models that are trying to capture how our economies adopt new technologies and the role of actors and people in making decision choices about which technologies to use. People have used this to try and understand the uptake of electric vehicles, of things like solar photovoltaics, etc. It's one of the kind of widely used methods in the field. Quite a different approach to the ones previously. Another one which is less widely used is to think about things from more of a kind of geometric or set theoretic position. So these are simplical complexes, which are a geometric structure, which people have used quite heavily in things like transportation modeling to understand the flows of vehicles through systems with varying levels of constraints. You can apply the same kind of thing to any other set theoretic relationship. You could take it something like social practice theory, and you could look at basically the sets of behaviours which go into construct a social practice, and you could map that onto a geometric construct, and then you could look at the capacity to move between these different practices on that kind of backcloth or fabric. So that's kind of coming out of a more qualitative social theory position and trying to think what is the appropriate mathematical structure that would allow us to represent that. And so it's quite different from the kinds of more standard statistical data-driven approaches we've seen, and it's more about trying to understand what the structural limitations of the relationships between these groups or sets would be. So that has, there's been some recent papers, this 2019 paper that's gone back to that. It's an old idea. Casti talked about it in Reality Rules, but then it hasn't seen much application until more recently. Moving on to ones about sort of causal knowledge models. So this should be probably more familiar ground. We're now sort of getting on to thinking about graphical statistical models like Bayesian networks. This is an example from a model that was developed, which I mentioned earlier, is embedding Bayesian networks within a Delphi process. So it's trying to take a standard qualitative Delphi process of eliciting expert opinion from a group, but it's intermediating that with feedback from a Bayesian network structure. So in the traditional sort of Delphi process, you have these rounds where you get experts to contribute their ideas, they share their ideas, they reflect on what they've learned by interacting with others, they update those, and they go through these cycles. And this interposes this Bayesian network structure, which says, this is how we think you are collectively thinking. Please reflect on this graphical structure and see if you agree with it. We can modify it. We can update the structure or the weights within the nodes. So I think this is a really rich area, because I'm of the belief that a lot of the time we can't model, if you like, from a kind of top-down theoretical position, how people will behave. We've tried to do that. A lot of times with energy, it's incredibly contextual. It depends on, the age of the building you're living in. It depends on your family structure, how far your school is, whether you can park your electric vehicle outside your home and whether you've got a charging station nearby. There's sort of tens of thousands of things which can shape the outcome. And throwing a kind of high-level economic or social theory at it from top down doesn't work. But trying to elicit those understandings from the bottom up, I think, is a really interesting and rich approach. So I think there's a lot of work that could be done on this. This leans into work of Nancy Cartwright, who's doing a lot of work on theories of change, which policymakers use a lot, and trying to look at how can we use the language of causal modelling within theories of change to develop a policy evidence base that we can have much stronger belief in the outcomes. So some really nice work by Nancy Cartwright that's going on, that she's active in this area at the moment. Somewhat related to that is kind of what you might call learning theoretic approaches. So this is taken out of a paper, it came out of one of the IEEE transactions on power systems, but it's kind of a nice illustration of what you can do. So what they effectively did is they built literally a simulator of a kind of energy network control room. So in the UK, our National Energy System Operator has a big control room, you might have seen photos of it, where they control the flow of energy around the UK. So what they did is they built a simulator, a bit like an aircraft simulator of that, and then they put human participants into that simulation environment, but they also put various forms of computer agents in that simulation environment. And they tried different types. So they tried ones that were trained just based on historical data. They threw in some which were based on a first principle analytical model. They threw in some which were kind of generative transformer-based models using generative adversarial networks. And so you had this population of different agents trained in different ways sitting alongside humans. And they were operating in this simulation environment. And then you get simulation results and you can compare and contrast how the different agents behaved in relation to the humans. So again, it's a really interesting structure. You can then capture the behavior of the humans from these environments and feed them back into model construction. Again, an extension of this is an approach called companion modeling, where this came out of environmental resource economics, where they worked in communities, particularly areas where you might have, say, an environmental area where you've got a hydrological basin and you're trying to capture how the behavior of people within that ecological system impacts river quality health or crop yields or other things. And they developed a method using role-playing games. So they would do a simulation of that in terms of a game that people in that community can sit around and play. And then what they did is they used that as the empirical basis for capturing behavior and using it to train an agent-based model. So rather than coming in with some assumptions about how people act, they observed by constructing this model within a model. So the role-playing game is itself an abstraction, it is itself a model, but then you can interact with the people. It's a very easy model for humans to understand and give you feedback and critique on, and then you use that to train your ABM. So again, it's a very different approach to linking data to models and what we're trying to achieve. So that's a kind of fly through of some really quite different approaches. In practice, people will often combine these different approaches into interesting hybrids. And I think that's where you have to be embedded in a research design. So you're thinking about, what are we trying to do? How do we interrelate our data collection through our modeling into the claims that we can make about the world? And yeah, each of these is coming from a different approach and has different kind of objects that sit within that in terms of mathematical constructs. There's a section in the kind of background reading that was put together which basically goes into this question of epistemic warrant. And I actually think from an interdisciplinary perspective, this is one of the most important things that we should be thinking more about. So what types of claim can we attach to our different modeling formalisms about the world? And so, we can go in with optimization models, but they're predicated on potentially things like revealed preference data collection. They're predicated on assumptions about people being rational actors and trying to find some kind of best possible solution. So they can have this kind of, it's easy to slip between looking at sort of normative outcomes and optimizing around a given outcome compared with trying to understand how the world is actually working. So strengths and weakness of those. Probabilistic, again, we can talk about what claims they can make. Can they make causal claims? Well, Judea Pearl and others have put a lot of work into trying to understand the grounds on which graphical models are capable of making causal claims. But there's a big literature around what we can do there. I won't go through each of these, but basically it's quite a useful section in the reading which digs into this. And this is stepping sideways into the philosophy of modeling and the claims we can base on that. ABMs, which myself and my colleagues have wrestled with quite a bit. The idea there is this claim of kind of generative sufficiency, that there is, we can build a model which appears to give an output which looks similar to what we observe in the world. Big questions about underdetermination. There's usually lots of configurations which could produce the same observable output. And it's very unclear how you work out which of those possible sets of combinations is, quote unquote, a more faithful representation of the world. So each of these has strengths and weaknesses. And I think the really important thing is just to understand what those are. There is no real kind of one ring to rule them all where we can just come up with one model that we collectively agree is the right way. In many contexts, you might want the legitimacy that comes from participatory modeling because that gives you a kind of social license and people are bought into that. And so you've got to be really quite clear about what are you trying to achieve as you go through. Similarly with model validation, you can't separate the question of model validation from the question of the kind of epistemic warrant. So how are we going to establish whether our model is a good representation of the world? Again, something I think, I said at the beginning, don't model it if you can't epistemically warrant it. So I think you really should start from, if I build this model, what claims can I make? What claims can I not make? Are they appropriate to the problem that I'm trying to wrestle with? And yeah, as I said, it's basically at the end of it, we have this suite of tools. I think it's really useful to be aware of quite a broad suite of tools, because I think a lot of the practical problems we're wrestling with, probably in modeling energy use, but also in many other applied areas, will end up with a mixture of rules. And these can be everything from modeling how people's beliefs update from the individual cognitive level. I have a colleague in UCL, Dave Legnardo, who's doing a lot of work thinking about how the sequence in which information arrives changes people's beliefs about the outcome. He does a lot of work in juries and trials and trying to understand how that sequencing, and that's basically mental models and how they update through to trying to come up with kind of mean field representations of whole populations. Both are perfectly valid, just be super clear the problem you're trying to solve. And I think, yeah, one of the interesting areas is particularly this question of thinking about embedding humans into models and kind of models into human decision-making processes. There was a lovely quote that stuck in my mind from some people who were doing computer games, and they said, we don't build computer games, we build games with computers in them. And I think there's an sort of analogy here is we should be building kind of research processes in which mathematical representations are embedded and trying to serve the outcome of that, and whether that's consensus formation or some kind of better capacity to predict or serve a normative end of understanding how we achieve a policy goal. Each is quite different. Here we are. I'm slightly early. I shall stop there. Bump. And yeah, I'm not sure I'll be able to answer any questions, but collectively in the room, we will probably be able to find somebody who can answer the questions.
Let's thank. So, any questions yet? I'll bring the mic over.
Thank you.